If concurrency causes all these problems, why not just run transactions one at a time? For decades, database designers assumed this was obviously too slow. Transactions would queue behind each other. A slow transaction would block the entire system. Multi-core hardware would sit idle. The conventional wisdom was that concurrency was not optional. Then, around 2007, VoltDB, built at MIT as HStore, made a surprising argument. Two things had changed. First, RAM had become cheap enough to hold entire datasets in memory. Second, OLTP transactions, when analyzed carefully, are extraordinarily short, typically microseconds, not milliseconds. Most of the latency in traditional databases comes from disk I/O and lock contention, not actual computation. If you eliminate disk I/O, everything is in memory, and eliminate lock contention, there's only one thread. What's left? Pure computation. And pure computation on modern hardware is extremely fast. VoltDB processes tens of thousands of transactions per second per core, single-threaded, with zero concurrency overhead. Redis uses the same model for its atomic operations. The book notes that VoltDB calls stored procedures partition procedures. Each one must complete within a single partition to maintain the single-threaded guarantee. The constraints are real. You can't have interactive transactions that wait for human input or external service calls. Everything must be precompiled as stored procedures. Long transactions stall the pipeline. Cross-partition transactions require coordination and are expensive. But for workloads that fit the model, short, predefined transactions, dataset fits in RAM. Actual serial execution delivers perfect serializability at high throughput. The simplicity is the performance. No locks. No deadlocks. No concurrency bugs. One thread, one transaction at a time. Two-phase locking, or 2PL, is the isolation algorithm that most databases used for decades to implement serializability. Understanding it explains why serializability has a reputation for being slow. The algorithm is straightforward. Transactions acquire locks on every object they read or write. Reads require a shared lock, compatible with other shared locks, but blocked by exclusive locks. Writes require an exclusive lock blocked by everything. Once a transaction releases any lock, it can never acquire another. This two-phase structure, growing phase, then shrinking phase, is what guarantees serializability. The critical difference from optimistic approaches: in 2PL, if transaction A has a shared lock on a row and transaction B wants to write it, B must wait until A commits or aborts. If A has an exclusive lock, B must wait for everything. This blocking is not a bug, it's the mechanism that enforces ordering. To prevent phantoms, 2PL uses predicate locks. A predicate lock covers all rows matching a where clause, even rows that don't exist yet. If transaction A is querying all bookings for room 123 on Tuesday, a predicate lock covers that condition. Transaction B cannot insert a row matching that predicate until A commits. Predicate locking is expensive. Checking every predicate against every write is O(n*M) work. In practice, databases use index range locks, a coarser approximation that locks an entire index range rather than a precise predicate. Slightly less precise but much cheaper to evaluate. The performance problem with 2PL is that it can cause massive lock contention under heavy write workloads, and deadlocks, where two transactions are each waiting for a lock the other holds. Deadlock detection and resolution add overhead. At high concurrency, 2PL throughput collapses. This is why many databases defaulted to weaker isolation levels rather than pay the 2PL cost. In 2008, Michael Cahill published a PhD thesis at the University of Sydney that would change how databases implement serializability. His insight: snapshot isolation almost achieves serializability. It fails only when a transaction's premise, the snapshot it read, is invalidated by another transaction's right before the first transaction commits. What if the database tracked those premise invalidations and aborted any transaction whose premise was corrupted? That would give you serializability without acquiring any additional locks. This is Serializable Snapshot Isolation, or SSI. It was implemented in PostgreSQL 9.1 in 2011, the first major database to ship SSI as its serializable isolation level. Here's how it works. Every transaction runs on a snapshot, exactly as in ordinary snapshot isolation. Additionally, the database tracks two things: which transactions read what data, the premises, and when a committed write affects data that a running transaction has read, a premise invalidation. When transaction B commits a write that would have changed what transaction A read, the database notes that A's premise is stale. If A then tries to commit, the database aborts it. A must retry. The key insight: this is optimistic concurrency control. Transactions don't acquire extra locks. They proceed as if there's no conflict. The database only intervenes at commit time if a real conflict occurred. Under low contention, which is the common case for most workloads, SSI performs nearly as well as plain snapshot isolation. Under high contention, SSI aborts transactions more aggressively than 2PL. But the book argues this is the right trade-off. Rather than holding locks that block other transactions, you let them proceed and abort the unlucky ones. The database stays live and responsive. SSI represents the state-of-the-art, full serializability with a performance profile much closer to snapshot isolation than to 2PL.